Good afternoon, everybody. And this I'm going to make a video, and this video is basically only for the UG student, not PG student. Okay, and and I'm going to give you the basic idea about the semiconductor. Okay, why semiconductor is necessary, why it is called semiconductor, what is the technical difference between semiconductor and metal, and as well as insulator. So everything we have to know if we want to understand the diode, application of diode, circuit analysis, as well as transistor, field effect transistor, MOSFET, GFET. This is, if we want to understand all this phenomenon, all this device mechanism, then we have to understand basic building block of all transistor, which is semiconductor. Okay, this part as per the syllabus, this is, I am not going to cover whole the part, yet I am giving you the basic idea about the semiconductor. Okay, so first of all, we will discuss few important things I am highlighting here. So basic introduction, basic semiconductor, next career in semiconductor, and nature of the career, and for density of state, these four things we will discuss here. Okay, first we are going to discuss the basic semiconductor. Why it is called? Normally what happened? Normally since we are going to discuss the electrical phenomenon, we mostly focus on the free electron available in a solid crystal. Okay, in semiconductor, normally what happened? In metal, the electron concentration is about almost approximately 10 to the power 28 electron per cc, per cubic meter in metal. Okay, but in insulator approximately 10 to the power 7 electron per cubic centimeter. These are the free electron available in insulator as well as metal. Metal is the number of electron is very high as compared to the electron in insulator. In semiconductor, what happened? Semiconductor electron concentration fall in between these two solid. Okay, is less than this and greater than this, and behavior of semiconductor is totally different from metal as well as insulator. Sometimes when temperature is zero, at 0 degree Kelvin, semiconductor behave as a insulator. But one thing remember, but semiconductor never, it may behave as if it is metal, but it never be converted into the metal. Okay, this is the basic things, this is the basic definition, but we have to understand more than that. Next, so what type of material, how can you identify which one is a semiconductor, which one is a metal, which one is the insulator? How can you identify? Suppose in atomic level. And number one. Number two, why we always focus to understand the atomic structure, electronic structure? Why? Because it is simple. See, if it is suppose semiconductors, suppose if it is germanium or silicon, then in order to know the behavior of whole this device, suppose this is a device, suppose it is a diode. Diode is a combination of two semiconductor. Okay, this is you may consider this is a semiconductor block. Okay, if we understand the behavior of this whole block, then we have to analyze the minute particle associated with the semiconductor, or the atomic structure of one silicon. If we understand the behavior of atomic structure or electronic structure in atom in in this semiconductor, then we can analyze the behavior of this whole crystal, because this whole solid piece, this is a solid piece, is combination of only monoatomic crystal. Mono means single atom, either germanium or silicon. Okay, and that is why we always we have to know the basic structure, nature of atom, this all the atomic structure is very important. Okay, so group 4 element. Group 4 means periodic table. Group 4 element. Why it is called group 4? Group 4 element in periodic table always semiconductor. What are the group 4 element? Carbon atomic number 6, electronic structure 2 4. Okay, you remember silicon 14 2 8 4. Okay, germanium 32 2 8 18 4. SN, tin. These all are group 4 element. Why it is called group 4? Because this is a nomenclature, the group 4 element in periodic table. Why it is group 4 element? Because outermost shell electronic state structure consists of 4 electrons. That is why it is a group 4 element. Group 4 elements with valency electron is 4. Okay. Now these are, I am removing this part. Okay. I will discuss this part. Now you know that if it is outermost cell, suppose this is a nucleus, this is a K cell, L cell, M cell, like that. Okay, this is a 2 electron, this is a, there are 8 electron here, 18 electron here, then 4 electron. Suppose. Then if it is 4 electron, how many maximum fulfill is outermost first S2, twice S2. This is we will learn. Now I am not going to detail in discussion. So outermost cell we need another 4 electron. This is necessary. So condition, outermost cell required 8 electron. Okay. Now we have half fill orbit. Half fill orbit means 50% electron is already there. So it should be, actually we need to be 8, but we have already 4 structure. Then we have to borrow from electron from any other atoms. Okay. Now what happens? If it is less than half fill, suppose electronic structure is 285, suppose this is 5. So in that case, if it is outermost cell is greater than half fill, then what happens? It will accept electron from any other nearby atom. Okay. Then suppose and if it is 281, if it is less than half fill, then it will give this electron to another atom. But when it is equal to half fill, then it will neither give or taken completely from any other atom. It will sharing will take place. Suppose another silicon, only silicon atom 288 structure. Okay, and other silicon atom, suppose this is a crystal. Suppose this is a crystal, 3D crystal. This 3D crystal means this one. This n numbers of silicon. Okay, one silicon atom is surrounded by any other silicon atom. Then what happens? This electron has this will sharing will take place in between this. Okay. So this silicon atom neither give this whole 4 electron to this one, or this silicon atom give this 4 electron to this silicon atom. They never completely give the electron to any other atom. Okay. They will share, and finally 4 plus 4 it will make 8 electron. That means in semiconductor covalent bond is always take place. How, I will tell you later. Okay. Suppose in this case, if you want to understand, suppose sodium chloride. What is a sodium atomic number? 11. Okay, 11 means 281. Okay, less than half it. And chlorine 17. This is 17. This is 11. So this is chlorine 287. So this is greater than half fill. Okay, greater than half fill means it will not give 7 electron to any other atom. It will, because it is greater than half fill orbit. Half fill means 4 electron. It is 7. So it need one more electron. It will take from here. Because sodium is less than half fill, it can give this electron to chlorine, and that is why we always write sodium positive. One positive means 1 electron is given to any other atom. Okay, chlorine negative means chlorine take borrow any 1 electron from other atom. Okay, you understand? This is a sodium chloride, but here it is not form a covalent bond. But here is, in case of germanium, it form a covalent bond. Why? Because sharing necessary. Okay. Now we will start. We will see the basic structure of it. What happened in it? This is suppose this is silicon or germanium. Oh, whatever it is. This is a semiconductor. Group 4 element. Silicon, germanium, arsenic, carbon, tin, SB, SN, all are group 4 element, all are semiconducting behavior. Okay, this is how we can identify which one is semiconductor, which one is metal. Suppose, how can you identify a metal? Suppose I am giving you example copper. Copper, atomic number 29. Okay, 29 means 2, 8, 18, how much? 10, 28, 1. Now, this one electron, why it is called metal? One electron is very, very far distance away from the nucleus. See, this is nucleus, this is K cell, this is L cell, this is M cell, this is 2 electron here, 8 electron here, 18 electron here, and 1 electron in this cell. This 1 electron is a longest distance from the nucleus. Therefore, shielding effect is very, very less. Shielding effect means attraction between nucleus and nucleus is positive, this is like negative. Then because it is very long distance from the nucleus, so the attraction of this electron and nucleus is very, very less, and this electron almost considered as a free electron. Okay, so in metal, one free electron available. Similarly, you can another example, silver, Ag silver 47, one odd pair electron is there, one odd pair electron is there. This is how we can identify these are the metal. Okay, if it is outer valence electron is 4, then it is called semiconductor. Now, structure, atomic structure. How it is atomic structure? Why it is necessary? In order to study the behavior of this crystal, big crystal, suppose a solid sugar cube. Suppose sugar cube is to look like this. Okay, then you have to understand the constituent containing particle, containing a tiny individual particle. If we analyze the atomic behavior or electronic structure, then we can characterize the electrical behavior of the whole crystal. That is why we are focusing on the atomic structure or electronic structure. Okay. Now this germanium atom, here n numbers of germanium atom is there. Okay, this is a crystal. Crystal means, you may confuse what is called crystal. Crystal means regular arrangement of atom. Suppose if you sit inside a class, okay, in every bench 5 students like this. This is a regular array of regular array of the student. And in crystal what happen? In ideal crystal what happen? Ideal crystal atoms are arranged in a regular array. Okay, regular array means you can understand from here. Suppose this is a germanium. This is 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 it. And extended. You can extend it. We don't know n numbers of germanium is there. All germanium atoms look like this. Now, germanium. Why I am drawing this? You can understand. What is the electronic structure? This is why I am writing blank, because there is another germanium and another germanium, and look, it just goes to n numbers of germanium. Okay, that is why I am not drawing whole the crystal. I am just make you understand what is the electronic structure, why it is necessary, and how we can understand. Okay, this is how germanium n numbers. This is combined with this. This is, and goes like this. I am not going to draw whole this picture, only to make you understand. Now, germanium is 32. Germanium is 32 atomic number. Okay, what is a 2A 18 4? So 4 electron will be here. So okay, 1 electron 1 2 3 4. Okay, clear? 4 electron this one. And this germanium atom have 4 electrons. 1, 2, 3, 4. Okay. This germanium atom 4. 1, 2, 3, 4. Okay. This germanium 4. Okay. This germanium is similar. All are identical germanium. So it will have 4 electrons. Now you see. This is the middle portion if you understand. This germanium is a 4 valence electron. 1, 2, 3, 4. Now there is another germanium here also. This germanium also share. This, how many electron you can see? 1, 1, 2, 3, 4, 5, 6, 7, 8. Okay, now electronic structure is filled up, so it become 8. So this bone is not known as a covalent bone. Okay, this bone, sharing bone, one electron shared by this germanium, one electron shared by this germanium. That is why it is represented like this. Okay, this is called covalent bone. In semiconductor, only covalent bone is there. Okay, clear? Now, now you can understand what is a hole concept and what is a electron concept. Okay, now what happened? This is a electron. If I remove the electron, then what happened? If I remove this electron is coming out. This is electron, and dot circle is represent electron. Okay, now this side cross circle means hole. This side is vacancy is created. Okay, and this vacancy is known as a hole. Okay, suppose if this vacancy, this is a electron, okay, blank circle means electron. If this electron moves to this vacant side, then what happen? It will be this, hole will move to here and electron move to here. Okay, but physically hole never moves. Suppose I am giving you another simple example. Suppose this is my table, this is a table, and two series this side and two series that side. Okay, and two person is sitting here this side. Okay, and this two blank series another side. If this two person sitting person moves from here to there, okay, from this side to that side, then what happened? it look as if the whole vacant share is moved here and field share is moved there, but practically whole never move. Clear? This is the concept of whole. Physical whole does not exist. Okay, only because atom as a whole neutral. To make it neutral, we always consider positive particle equal to negative particle, so that it will become a neutral. Okay, practically whole does not move. Okay, and whole current exists inside the semiconductor only. Outside the semiconductor, there is no question of whole current. I will discuss you later. Okay, this is called whole and this is called electron. This is the basic structure. Similarly, you can understand the silicon. If it is silicon, then atomic number silicon is 40284. Okay, if it is any other atom, germanium, silicon, SN, SB, carbon, all are group 4 element are semiconducting nature. All are semiconductor. Clear? Okay, basic requirement of semiconductor: outer valence cell must contain 4 number of electrons, so that it can share 4 electron with similar atom. Nearby similar atom, then it will form a covalent bond and then it become a semiconductor. Okay. Now the semiconductor divided into two groups. Semiconductor dividing into two groups, and this divided is based on band gap. What is now band gap? What is now you have to understand what is a band gap. So any gap in between two energy level. See, in energy scale, in microscopic scale or nano scale, whatever it is, microscopic scale means and very minor scale. Okay, low tiny particle analysis. In microscopic scale, energy level of the atom is a discrete. Suppose this is a energy level of a one particle, minute particle, microscopic particle. Okay, particle is just similar to the electron. Then energy level E1, E2, E3, ET. So energy level of microscopic particle is a discrete, and there is a gap in between the energy level. Okay, this gap is known as a band gap. Okay, clear? But in case of this is why this is band gap concept is necessary, because we are discussing a microscopic particle, for example germanium, silicon, like that. Okay. Now, but here band gap concept is different. Band gap in metal what happened? There is a two band gap. Now one is valency band VB and conduction band. Okay, Valency band and conduction band concept. Valency band is the band formed by electron closest to the nucleus, and they are not responsible for electrical conductivity of the semiconductor. Clear? Suppose I am giving another example. This is a nucleus, this is K cell, this is L cell, this is M cell. It goes like that. This is N cell, this is 2 electron, here 2 electron, here 8 electron, here 18 electron, here 1 electron. Okay. Now this 1 electron is very longest distance as compared to the electron in K cell, L cell, M cell, like that. So this electron, outermost cell electron, almost considered as a free electron, and this electron becomes as a free. Any electrical conductivity or any electrical properties of this disk atom or crystal containing this atom is responsible for this electron. Kill it. Okay. And this electron, these 2 electrons are normally they are not free electron. Why? Because this is electron 2, 8 electron very close to the nucleus. There was shielding effect, it's very high, so tightly bound. Okay, and this is a lessly bound. So this electron almost considered as a free, and because J, you have already studied J equal to NEVD. VD is a deep velocity, and is a concentration of electron, E is the charge of electron. Okay, when N is very large, N means free electron concentration is very large, then conductivity, J current density usually increases. So we are focusing on how many electrons available. Then we can analyze the electrical behavior. That's what I am going to study. So valency band is, what do you mean by valency band? You can understand from here, the band formed by closed cell electron. These are the 2 electron, 8 electron, 18 are very close. The band formed by this electron or this closed cell electron, any closed cell electron is known as the valency band. Clear? Conduction band formed by outermost cell electron is known as a conduction band, because this outermost cell electron almost considered as a free electron, and these will responsible for any electrical property of the material. Clear? Okay. Now I am telling again, band formed by closed cell electron is known as a valency band. Band formed by outermost cell electron, which is almost considered as a free electron, is known as a conduction band. Clear? Okay. And for this is a atomic structure. Now how we graphically we analyze the band. How we analyze? So graphically, ideal structure. This is in books you will find. This is a valency band. This is a conduction band. Okay, clear? Now this is a gap. This is called band gap. Band gap. Now this is also known as a forbidden gap. Forbidden gap. Why this forbidden gap? Because electron cannot exist in between this. Electron either exists valency band or conduction band. All the electron in conduction band considered as a free electron. If there is no electron in conduction band, all electron are valency band, then it will behave as an insulator. Okay, there is no free electron, and there is no electrical activity. Clear? Now, this is a forbidden band. I am removing this part. Shortly I am writing forbidden band or band gap. BG, band gap. Clear? Now, what is our focus? Our focus, how can we increase the number of electrons? Our main aim is to, if you want to increase the electrical conductivity of this semiconductor, then our main aim is to increase the number of carrier from valency band to conduction band. So how can you increase the valency band to electron in conduction band? We can increase. We have to give heat energy, or you can give a radiation, electromagnetic radiation, radiation energy, or heat energy, thermal, statistical physics. So if you heat this semiconductor, then electron from valency band to conduction band increases. As a result, electrical conductivity increases. But in case of metal, if we increase the heat or electrical voltage, if you give the voltage on a metal, then what happens? Initially, all electrons are random, average velocity is 0. When you increase the heat, what happens? All electrons are free electrons will collide with each other. As a result, this metal becomes heat, and heat, there is a loss of heat. Okay, I will discuss that part. Now, this is a valency band. This is a conduction band. This is a valency band. So why it is depending on the band, we divided the, this is the ideal structure. In books you will, actual structure is, band structure is look like this. This is a look like this. This is a valency band is this one, conduction band is this one. And there is a, in conduction band there is a different subatomic, sub-energy level. This is like this is an energy level. Because n numbers of electron will be there. So all electron will not fall, will not be in a single energy level. There will be different energy level as part of Pauli exclusion principle. Okay. Now this is ideal structure. I can write like this, okay? This is a practical structure. Why practical structure? Because this is nucleus. This is look like band structure, na? Band. That is why this look like that. Now, depending on band gap, the semiconductor is divided in two parts. One is a direct band gap. Direct band gap semiconductor. Why it is called direct band gap? Suppose this is a conduction band. This is a valency band. Now, if we give the heat to the semiconductor, if we heat this semiconductor, then electron this band is moved directly to the conduction. Okay. Suppose if you remember the hydrogen atom, what is the energy of hydrogen atom? Minus 13.6 electron volt z square divided by n square. This is the energy. This is the ground state energy. If we excite the hydrogen atom, then electron will jump to the excited state. Then we have to calculate energy in excited. Similarly, here also, when you heat the semiconductor, electron from valency band move to conduction band. And this gap energy is represented, this is the gap energy is nu or is C by lambda. Clear? This is a formula. Now, this is a happening direct band gap. Direct band gap are, which are the direct band gap? Remember, direct band gap are compound semiconductor. Compound semiconductor, indium phosphate, gallium indium, phosphate. This is a compound semiconductor. Why this compound? Because this semiconductor consisting of two different type of atoms. One is germanium, indium, one is phosphate, and one is gallium, one is indium. Gallium arsenide, gallium, indium, phosphate. These are the compound semiconductor. These are the direct band gap semiconductor. Okay, and this is always happen group 3, group 4 element. I will discuss later. And this is direct band gap semiconductor. Okay, now I am considering indirect band gap semiconductor. What is the indirect band gap? Second, indirect band gap. Indirect band gap, what happened? You see the indirect band gap. This is conduction band, this is conduction band, and this is valency. So electron move here. And this is indirect. This is called tap center. Okay. What happened in indirect band gap? When you take an indirect band gap semiconductor, and indirect band gap semiconductor monoatomic, this is germanium, silicon, arsenic, this type of monoatomic semiconductor are indirect band gap semiconductor. Indirect band gap semiconductor, what happened? You try to understand. When you hit this semiconductor, the electron directly, it will not move to the conduction band. Okay, it will move to the tap center. Okay, then it will move with the conduction band. As a result, what happened? The response after few nanosecond or picosecond, this electron move to the conduction valency band. Because everything in the universe try to minimize the energy. So if you want to minimize, you have to lose energy. And how can you lose energy? If we electron in conduction band, initially it is valency band, we heat it. When we heat the semiconductor, electron move from here to tap center and then conduction band. After a few seconds, it will go back to the valency band and giving the radiation. Okay, radiation. Suppose energy, it will radiate energy. Suppose LED. LED is happening like this. Okay, I will discuss that part. In indirect band gap. As a result, what happened? The response in direct band gap, what happened? This is a direct band gap, valency band. It will directly move to the conduction band, and again when you remove the heat, when you cool the semiconductor, again electron from conduction band get down to the valency band. As a result, response of electron, response means time between moving from valency band to conduction band and conduction band to valency band will take larger time as compared to the direct band gap semiconductor. This is the indirect band gap semiconductor. Indirect band gap semiconductor, these are monoatomic crystals, are indirect band gap semiconductor. As a result, the performance of direct band gap semiconductor is more better than indirect band gap semiconductor. Why? Suppose I am giving an example. Suppose you are sitting in front of a TV. Suppose you have a remote. Okay. Suppose remote is made by the direct band gap indirect band gap semiconductor. Then what happens if we push the 5 button? Then after few minutes or few minutes, the channel will change. And in this case, what happens once you push the button, TV button, remote button, then quickly the channel will change. Which one is better? So direct band is better than indirect band gap. Clear? Okay. And direct band gap elements are compound semiconductor, indirect band gap semiconductor, monoatomic crystal. Clear? You understand? I hope you understand. This is the basic. Anything else? No. This is depending on the band gap. Next, we consider type of carrier. Now, depending on type of semiconductor, what type of, depending on the carrier concept. I have already told the whole concept, electron concept. And in semiconductor, there is a 2 carrier. One is called hole, which is represented by H or P. Okay. And one is represented by electron or N. N means number of electron carrier concentration, and hole means represented by P. Okay. In semiconductor, there is a hole as well as P. Okay. Depending on the carrier concentration in semiconductor divided into 2 parts. One is depending on, this is depending on carrier. Okay. Depending on carrier. One is intrinsic semiconductor. Intrinsic semiconductor. We know intrinsic semiconductor, we always represent like this. And extrinsic semiconductor. Okay. This is known as a dominant semiconductor. Why it is intrinsic? Intrinsic semiconductor means the equal whole and equal carrier. And how can you define? You do not define the intrinsic semiconductor as semiconductor in which number of carrier, number of hole equal to number of electrons. This is not the actual definition. Intrinsic semiconductor is a semiconductor which is purified in such a way that number of carrier equal to number of hole. Why? I am giving an example. Suppose this is my table. Suppose you see the diagram. This is a table. This is in my room. 2 chair. This is a 1 chair. This is a 1 chair. And this is 1 chair, this is 1 chair. Okay? And this is electron. See, this is my room. This is my room. This is door, suppose. This is door. Okay? Door is this one. So, this is an intrinsic semiconductor example. Suppose this is a table and 2 chair is this side, 2 chair is this side, 2 chair, 2 person means electron is sitting here. Okay? Now, this is look like that. Number of electron equal to number of vacant chair. So equal 2 chair is fill up chair and 2 is vacant chair. So if this is the electron then if it is represent a hole. Provided one condition, provided there must not be any person be inside the room. Otherwise, if this is a suppose bed. If somebody is hiding inside the bed, he will sit here. Then what happens? Number of electron will not become number of hole. Okay, that is why definition is like that. The intrinsic semiconductor is purified in such a way that, so that this is a suppose intrinsic semiconductor, suppose germanium or silicon. Okay, it is purified, it is made in such a way that in a laboratory that there is no impurity. No impurity means what I am giving here example, any person hiding inside the bed. So any person, if unknown, without my knowledge, if somebody hiding inside my bed, that is considered as impurity. So the semiconductor which is purified in such a way that there is no impurity and number of hole equal to number of carrier. Okay, this is intrinsic semiconductor. And this is a dominant semiconductor. Why it is called dominance? If the number of this is greater than P, if one condition, if the a semiconductor, this is a semiconductor, this is a compound semiconductor, if the electron concentration is very, very high as compared to hole concentration, then it is called the N-type. And if P is very greater than N, then it is called P type. Clear? This is a dominant semiconductor. This is a depending on the carrier, and previous one is a depending on the band gap. This is a two classification. Probably you have already encountered in ACES also, but you have not encountered so much about the band gap structure. Okay. Now, why it is called N type? N is very greater than P. I will discuss it later. Now our focus is we have already understand what is the whole concept, what is the electron concept. And now what is our aim? Our aim is to, if we want to know the electrical behavior, for electrical behavior means voltage, current density. If we know what is the performance of this semiconductor, then we have to understand how many number of electron available in conduction band, and how many hole is available in the valence band. Why hole? Hole means vacancy. So if you know the number of vacancy inside my room, then you can easily tell that how many person you can accommodate in my room. That is why we have to understand number of vacancy. Vacancy means hole, and you have to also understand and how many person available in outside your house. Both you have to know. Then if you 80% is sitting in front of my house, then I have to know how many vacancy are inside my house. So I have to know number of person outside my house and number of share available inside my house. That is why in semiconductor we have to know number of hole and as well as number of electron. Okay. So in order to understand that, in order to calculate number of carrier in semiconductor, maybe either hole or electron, we have to know the density of state. Density of state is very important. In statistical language, it is known as the number of microstate. Okay, number of microstate means how many number of vacant site is there. That's what you have to know. So if you want to calculate the number of carrier, either electron or hole, whatever it is, in semiconductor, then you have to understand the density of state. And density of state formula is very essential everywhere. If you know the density of state, you can easily understand statistics. If you know the density of state, you can easily understand condensation matter physics. If you understand density of state, you can understand quantum mechanics. All related to density of state and black body radiation. So what is the density of state? Density of state. Or in statistical language, it is called number of microstate. In quantum mechanics, it is known as a basis vector. Okay, this is the language is different and representation is different, but the concept is same thing. Okay. So in order to calculate the density of state formula, we have to understand the phase space. Okay. Now phase space. What is the phase space? Phase space. In order to understand the density or in order to calculate the density formula, you have to understand phase space, not phase space. Phase space. So n Cartesian space. What is the Cartesian? Cartesian space means rectangular space. Rectangular space. What is the rectangular coordinate? X, Y, Z. X, Y, Z means it will have three axes, X, Y, Z. This is a rectangular space. And what is the phase space? Phase space is three-dimensional. Okay, remember. And phase space, this is X, this is Y, this is Z, and there will be Px, and this is Py, and this is Pz. So phase space is 6-dimensional, remember, and rectangular space or Cartesian space is 3-dimensional. Now suppose this is a rectangular space. I am drawing here again to make you understand. Suppose if you consider point P, arbitrary point P in space. Suppose this is my room, this is 3-dimensional room, this is x-axis, this is y-axis, this is z-axis. If I take a point here, then if we want to understand mathematically this representative point, then what are the coordinates required? X, Y, Z. Okay, this is known as the representative point in Cartesian space. But here, if I represent the same point in phase space, I will need x, y, z, px, py, pz. This is a momentum. This is px is a corresponding momentum with respect to x, py is a corresponding momentum of y, pz is a corresponding momentum of z. And this point is represented by q. Because we don't have so much time, then we normally write as a q, and this point is represented simply p. Or we can simply write p point is represented q, p. This is called representative point. Clear? This is a representative. This is we can simply write q also. Q means q equal to x, y, z. T coordinate is already exists. This is for single particle. Clear? Now, in Cartesian space, if we want to represent a single particle in rectangular space or Cartesian space, we need 3 degrees of freedom for single particle. If there is a n numbers of particles in rectangular space, we need how many degrees of freedom? How many coordinates? See, so this is first particle. This is second particle, x2, y2, z2. This is dot pn particle. How many? This is I can represent p q q1. Okay, p simply p q2. This is p. How many number? N numbers. xn, yn, zn. How many coordinate? Thyssen coordinate will be 3, 1 3, 2 3, Thyssen. That means for n, if the system is, suppose if I have a system, this is there are n numbers of silicon atom. If I represent n numbers of silicon atom in Cartesian space, I need a Thyssen number of degree of freedom, means Thyssen number of coordinate. Okay, and these all are x, y, z. But here, how many number of coordinate? Thyssen momentum, Thyssen position, and Thyssen momentum. Total 6 n number of coordinate required. That is difference between Cartesian space and rectangular space. And number 1. Number 2, this all px, x, y, z, px, py, pz all are mutually perpendicular to each other, just like x, y, z. Clear? Okay. This is a basic definition of phase space. I am drawing it again. Phase space, sensitive state I am going to calculate. Remember now. In Cartesian space, this is a Cartesian space. If I take a small cell, okay, small cell. So if I take a small cell, how many points? This is it. Suppose this is x, this is y, this is z. Okay, you can take any arbitrary. This is small cell. This is dx, this is dy, this is dz. Clear? What is the volume? Volume is a product of all dimensions. Means dx, dy, dz. This is in Cartesian space. Small cell. Why we need small cell? Suppose, and this is my wall. Okay. Okay. If I want to know how many eta will be required, then what I have to do? I have to measure I know the height of this wall. Okay. Height of the I have to build up. Okay. Then in that case, I have to know the volume of one single eta building block. Then I can know how many eta will be required. So similarly, I want to know the small cell in Cartesian space, which is represented by dx, dy, dz. And because I have already told, I simply write as a dq. dq means dx, dy, dz. It contains 3 coordinates. Similarly, suppose in this is a phase space. This is Cartesian space. Cartesian. This is phase space. Phase space. This is suppose px. This is how many lines are? This is x, this is z, pz, x, px, y, py. If I take a small cell, what is the volume of this here? What is the volume? Phase space volume. Then, according to the here it is 3 dimension. Here it is 6 dimension. Dx, dy, dz. We have to take the product of all dimension. In here, what is the volume? We take the product of all dimensions, right? dx, dy, dz. Here we have, if we take the small cell volume in phase space, then we have to take the product of all volume. dx, dy, dz, dz, dpx, dpy, dpz. Clear? Okay. This is the basic understanding of phase space. Now forget about rectangular space. Now volume in phase space, unit cell volume in phase space. Okay, it is very important. After that I will finish that part. Okay, unit cell volume, what is represented? dV. Okay, unit cell momentum space, dx, dy, dz, dpx, dpy, dpz. Clear? Now you see, now dx, dpx, this is position, this is corresponding momentum. You can consider as a error, small deviation or error. Okay, similarly d and dy, dpy, dz, dpz. According to Heisenberg principle, what we have learned, del x, del p almost equal to h. This is from Heisenberg principle. Error in position, measurement, error in momentum. Or we can simply write dx, or we can write dx, dpx. Why here dx? We are representing in terms of derivative term. This is represent small change, small volume or error. This is equal to h. So this will become h into h into h equal to h cos. So unit cell volume in phase equal to h cos. Remember. Okay, you understand? Now this is a unit cell volume. What I am getting is Q. Okay. Now why I need unit cell volume? I will suppose this is my room. Again I am telling an example. This is suppose chair. I want this is suppose chair. This is n numbers of chair is there. Okay. What are the information I need to find out? First of all, I need to find out what is the volume of this chair. Okay. Next, what is the volume of my room? Or what is the free space available in my room? Okay. If suppose this is suppose 200. Okay. Number of this is 20 number of chair is there. If I divided 200 by 20, then what I will get? 0, 0, 0, 10. 10 is the density of stack. Okay. Now I am calculating the small cell volume in phase space. Okay. Now I am going to calculate the total volume of phase space. Both are equal. So total volume is dV. I am writing again dx, dy, dz, dpx, dpy, dpz. This is for a single particle. Remember, don't confuse. This is only for a single particle. Okay. And if I write simply, I can write this because this is q. I can write dq also. Okay. Do not confuse in a book. In book that is represent dq into dp. Then I will write this one q. Why I write q? This q, t is not power. It represents 3-dimensional. 3-dimensional Cartesian coordinate, 3-dimensional momentum coordinate. Now I can write, or if you confuse, don't write. I will tell you later. If you confuse, you simply write dp, dq, or dp. Do not write if you confuse. Now what is the total volume? V equal to integration of dv. You know this integration formula. Okay. Integration. Then what happens? dx integration, dy integration. Because this is a volume integration. Volume integration will be with respect to x, with respect to y, with respect to z. dz or this dpx, dpy, dpz. Okay, this is simply I can write dv in rectangular volume. Okay, correct. And this is I can write dp. I have already told that. Okay, or you can write dq q and dq p. Why dq? This is a 3-dimensional small cell. And 3 means it is not power, it is represent 3-dimensional. And q means x, y, z. Clear? Similarly, this momentum, 3-dimensional momentum. Okay. P and P means px, py, pz. And 3 means 3-dimensional system. Then it will give, we don't know, this will give volume. Volume we don't know. It may be L cube, A cube, A square by A square. If it is square, we don't know. That is why simply this is a rectangular volume. Okay. In this will give a now question. What is the volume of momentum? This is a momentum space. Momentum space is always considered as sphere. So that is why we write always momentum volume PQ. Clear? Now total volume of phase space equal to how much? Total volume of phase space is represented by V. This is total volume, okay? If you confuse, then Vt, you write Vt. This is a rectangular volume into 4 by 3 by PQ. This is the total volume of phase space. Clear? From where I am getting? This simply write 3 4 pi V PQ. This is the total volume of phase space. Okay. Now I have to calculate number of microstate. Okay. Now number of microstate or density of state. How can you calculate? This is very, very important for competitive examination like JAM, NET, GATE. Also, if you confuse, I have a lot of video on my YouTube channel, and for a competitive exam you can see also what type of question comes in exam. So density of state, I simply write density of state. Okay, don't confuse, I am not going to write it again and again. Density of state. So density of state is, first I will calculate density of state in between 0 and momentum P. I have to calculate. Suppose this is my room, this is a 0 axis, and suppose this is 100 meter. I will calculate the total number of vacancy available in between 0 and 100 meter. First I will calculate it. Similarly, in microscopic cell, it is present number of microstate in between 0 and momentum P. I will calculate first, then I will move directly. And this is represent by P. P, why I am writing P? Because this P means it is function. Don't confuse sigma into P. Sigma is the density of state. Okay, it is a function of P. Function of P means this sigma depend on momentum. Equal to what I am getting? Total volume Vt into divided by small cell volume, right? Small unit cell volume. What is the unit cell volume? Unit cell volume, this one. Clear? So total volume, what I am getting? Total volume 4 pi V by 3 PQ, right? Divided by S cube. Okay, equal to, you will get 3 S cube 4 pi V PQ. This is known as the density of state in between momentum P and P plus D. This is very important. Clear? Okay. After that, now question is that, now what is the question in semiconductor? There we are talking about electron. We are talking about hole, which are the fermion. Then that means I have to find out the density of state for fermion separately, as well as some particle, suppose phonon. Specific heat you have already studied. Specific heat solid is occur due to mainly due to the phonon. In that case, phonon is a boson. So in case of boson, the density of state will be different. I will discuss later. Up to that, you try to understand what is the density of state. Okay. Okay. Thank you. I hope you will understand, because online class using the Google Meet or Zoom, it is not possible because non-availability of good network, as well as a lot of limitation, data rate, and that is why I make the video so that you can understand. Okay, if you have any question, you can send any message, any query in the WhatsApp group. Okay, thank you.